Chemical Kinetics Part 10, Half-Life Introduction and Half-Life for a Zero-Order Reaction. Here's a sheet with all of the important equations that you would need to do calculations for chemical kinetics. In this video, we're going to take a look at how you can take the integrated rate law for a zero-order reaction and turn it into the half-life equation that you see right here. So first of all, what is half-life? Let's say we have a simple reaction where A turns into products. We have a single reactant. We could say that the half-life, or T subscript 1/2, we'll say T 1/2, is the time when the concentration at that time is equal to 1/2 of the concentration at time 0. In other words, 1/2 of the initial concentration. Now remember that chemical A is a reactant, so as the reaction progresses, the concentration of A will be getting smaller and smaller and smaller. So when the concentration of A is equal to half of what it started as, you have a time of T 1/2, a half-life. So if you start with 50 grams of a chemical and it takes 10 minutes to get to 25 grams, half of 50, well, that means that 10 minutes is the half-life. Let's take a look at half-life for a zero-order reaction. And we're going to do this for all orders of reaction by starting with the integrated rate law. This is the integrated rate law for a zero-order reaction. And we're going to pretty much do the same thing over and over, just using a different equation to start with. What we do is, knowing that the half-life is the time at which the concentration is half of the initial concentration, we're going to substitute 1/2 of the initial concentration, 1/2 of A at time 0, in for A at time t. So we just substitute this in for this. And from here on out, we're going to say that the time is the half-life. It's T 1/2. Now we just need to rearrange and simplify. Let's add positive K T 1/2 to both sides. So it cancels out here and it appears on the left. And let's subtract negative 1/2 concentration of A at time 0, or negative 1/2 initial concentration, from both sides. Now take a look at this right side. Any value minus half of itself is going to be equal to half of itself. So the concentration of A at time 0 minus half the concentration of A at time 0 is going to be half of the concentration of A at time 0. Divide K in both sides, so it disappears on the left and it goes in the denominator on the right. And we end up with T 1/2 is 1/2 times concentration of A at time 0, or we could say 1/2 times the initial concentration divided by K. Let's put that 2 in the denominator to get this final result. This is the zero-order reaction half-life expression. Notice that the bigger the initial concentration, or concentration of A at time 0, the bigger, the longer the half-life T 1/2. That's true for a zero-order reaction.